Hello, and welcome to A Gross of Physics. Today is day 24, where we're going to look at actual problem solving for projectile motion problems. And the most important thing that I've found is using a chart to separate the variables. And I'll discuss how that chart is used, and we'll do a couple of sample problems today. We've been discussing all of this qualitatively up till now, just dealing with the concepts. Today it'll be a quantitative approach so that we can actually solve for problems and different variables within those problems. But remember, the most important thing to realize is that perpendicular vectors are independent. Since the x and the y directions by default are 90 degrees apart, they are perpendicular, and we're going to be able to treat the x and y directions as two separate problems. So you get two problems for the price of one. You think you're getting shortchanged before? No longer. I'm going to give you a 2-for-1 option today. Now, how are we going to solve these steps? At the beginning, I think it's important that you use these problem-solving steps, but remember, your goal is to develop your own problem-solving skills, and you may find a method that's slightly different than mine. But no matter what, in order to get full credit on an assessment, you need to have formula, substitution with units, and your solution. The intermediate steps are irrelevant, but you need those three things. For our purposes, though, I think the chart is going to be the key. Now, what I would do is set up a givens list for any of the problems. I would probably draw a diagram to at least visualize the problem at first. I would then have my chart set up and solve for the unknown in the direction that I have the most information for. T is the key. So, if I know more information in the x direction, I'll solve for time in the x. And then that time is going to be used in the y direction. I may only have two variables in one of the directions. In this case, if I have 3 for the x, I probably only have 2 variables in the y. If I find the time, that will be my third variable in the y direction, and I'll be able to solve for whatever unknown I'm looking for. A lot of times it's going to be the displacement of the object, but it could be something else. Final velocity, total velocity, maybe the resultant velocity at the bottom, and remember, bottom being in the air, because as soon as the object hits the ground, all bets are off because the acceleration changes. After that, I'm going to find the unknowns in whatever direction I'm looking for. But the bottom line is T is the key. That being said, I'm going to write my givens so that I have an x and a y distinction. I'm going to set it up so the x's are on the left and the y's are on the right. There's no reason I do x on the left and y on the right. It's just convention. I just do x and y because we often write points on a graph as x comma y. So I just go left to right. I'm going to list anything I know about the x direction, anything I know about the y direction. Some variables that are going to be common to most problems. In the x direction, we're normally going to have no acceleration, so ax will often be 0. And in the y direction, we're often going to have the acceleration of gravity on the Earth, so it's going to be negative 9.8 meters per second squared. Different things could occur. Maybe we'll have a projectile motion on the moon or some other planet. So that may change. Sometimes we may have wind resistance sideways. Maybe we'll have a fan acting. Maybe we'll have rocket shoes on the object or a rocket skateboard or something like that. So we may still have an acceleration in the x direction. But for the majority of problems, ax is 0 and ay is negative 9.8. But then we'll usually have t unknown, and I'll have t be my common variable for both sides. That being said, the chart is the most important thing that I've found to keep our units and our variables separated. We don't want x's mixing with y's. The only variable that can jump to both sides is t. So maybe we could think of the x and y variables as elementary school dance. All the boys are on one side of the dance, all the girls are on the left side of the dance. T might be the teacher, who is trying to get people to mingle, trying to get people to interact with the other gender. So they're going to go from both sides to try to, get them to all do the hokey pokey or some kind of dance like that together. But typically think elementary school dance. All the boys on one side, all the girls on the other. The teacher's trying to get everybody to mingle, but they really don't want to at that age. The T is the same for both sides. The same teacher is for all the x's and all the y's, all the boys and girls. I guess in this case, the x's would be the girls and the y's would be the boys if we're thinking about biology class. And if you don't know what that means, you should remember back into your chromosomes from bio class. What we'll do now is we'll look at some sample problems for the x and y direction, and we'll try to calculate some unknown variables doing some sample problems. Thank you. All right, for this problem, what I'd like to do is solve a horizontal projectile motion problem. And what we're going to do is determine a marble rolling off a table. And the question ends up asking how far does the marble land from the table. So what we're going to look for is dx. Now let me read the problem. A marble rolls off the lab table at a speed of 4 meters per second. The table is 0.95 meters tall. How far from the table does the marble land? So that means the marble is going at 4 meters per second when it leaves the table. The height of the table is 0.95 meters. And we want to find dx. So the process by which we solve this is to start with a givens list, like we've done for many of our problems. But instead of just listing a single list, we're going to have two sets. We have x and we have y. Now, when we do that, we put all the x variables on the left and all the y variables on the right. For example, the 4. The v in the x, that's your 4 meters per second. And if all of the motion is sideways, that means there's none left over for the y. So it's actually 0. Now the second variable we typically look at is the acceleration. There's no sideways gravity, so we say that's 0 meters per second squared. And ay, because we're in the Earth's gravitational pull, negative 9.8 meters per second squared. There's a distance value, and that's your d in the y direction. So dy is 0.95 meters. However, since the object fell downward, we're going to need to use a negative 0.95 for that. The dx we don't know, so that's our find. Now, we only have 2 variables here on the x side and 3 on the y. So what we're going to do is determine the time in the y, and then that will be the same time that is true for the x. Now here's the hint that I like to use. This shape of the chart here looks like the letter T. So if I'm concerned about which variable is common to both sides, I'm just going to look at the chart itself, and that will give me the answer. The T is the variable that is common to both sides. Now, if I know V, A, D, and I'm looking for T, what I'm going to use is equation 4. So I'm going to write D equals VIT plus 1/2 AT squared. Negative 0.95 meters equals, that was 0, 1/2 negative 9.8 meters per second squared, t squared. I'm going to do 1/2 times 9.8. I'm going to divide it into 0.95. I'm going to do that on the calculator. So 0.95 divided by 4.9 is 0.1938. And that's going to equal t squared. I'll take the square root of both sides. Second answer. And I get t to be 0.44 seconds. So that means the time for both sides is 0.44 seconds. So now what I do is I go to the x direction. And sometimes to keep things straight, you could write a y here because you know it's only the y's. Maybe we'll put an x here. I use the same equation again. VIT plus 1/2 AT squared. And this is going to simplify because the acceleration is 0. So you're left with d, which is what we're looking for, equals 4 meters per second times 0.44 seconds. Now, of course, I rounded the 0.44, but since it's already in my calculator, I'm just going to type 4 times second answer, and I'm going to get my distance to be 1.76 meters. And that's all you need to do to solve a horizontal projectile motion problem. If you look, it's a lot of writing to show all your work. However, it's just a series of two problems with a common variable that happens to be t. Well, let's look at another example in a moment. All right, for this problem, what we have is a paper football being flicked off of the table and trying to land into the recycle bin. And the height of the table is given, the height of the recycle bin is given, and the distance the recycle bin away from the table is given. So all the distance values seem to be given. Some are in centimeters, some are in meters. And what we're looking for is the velocity that the paper football needs to be struck so that it goes into the bin. So it flies in the air and lands into the bin. So what we're going to do is realize that in order for this to happen, it doesn't have to hit the ground. It just has to go to the height of the bin. So the first step is to realize that you're only going to fall 73 centimeters minus 34 centimeters. Now, we could probably do that in our head, but I have my calculator right here. I'm going to verify that 73 minus 34 is 39. That's what I thought, but I wanted to make sure. I wasn't certain. So 39 centimeters. That's your y distance that it's going to fall. Once it's in the bin, it'll fall the rest of the way, but we're concerned with getting it into the bin. Now, that being said, we could start with our givens. We actually don't know Vx in this case, so we're going to set our givens list, our xy. We don't know Vx, so I'm just going to write Vx question mark, just so I keep my givens lists so the V's are together and the A's are together. Vy is 0 meters per second. Ax 0. Ay negative 9.8 meters per second squared. Then we have dx was 1.5 meters. dy negative 39 centimeters, so that's 0.39 meters. And what we're going to look for is t and figure out what v happens to be. Now, if I look, I know because I wrote it, I only have a question mark here. I don't know that variable there. So I have a and d for the x direction, 0, negative 9.8, and 0.39 in the y. So I think I know more information about the y direction. So I'm going to start there. I'm going to start in the y. I'm going to say d equals vit plus 1 half at squared. Negative 0.39 meters equals, that term cancels, 1 half negative 9.8 meters per second squared, t squared. All right, I'm going to solve for t. 0.39 divided by 4.9, the negatives will cancel. Second square root, second answer. I have t is 0.282 seconds. Now t is common to both sides, so this t and that t are even. So in the x direction, d equals vit plus 1 half at squared. Once again, this second term cancels, and I'm left with 1.5 meters equals v times 0.282 seconds. So v is 1.5 divided by, since it's still my calculator, answer, and I get 5.32 meters per second. So as long as it's hit with 5.32 meters per second worth of speed, the paper football should go into the recycle bin. Now, of course, we're neglecting wind resistance, and that would be to the front corner of the recycle bin, so it could actually hit the bin and pop out, perhaps. So it would be best if we made this a little greater. So the reality would be this is our minimum value, and then often we find the value that would cause some condition to be true at the minimum. Larger than would also work. What we could also figure out is maybe how far it would go to the end of the recycle bin, and then you'd have to be somewhere within the range. The problem with that is we have no idea how wide the recycle bin is. We just know the height. So we need to measure that first, and then we can find the full range. That would be a good problem too. But this is the answer to the problem we were asked now.